Hydrofluoric acid or HF corrosion, risks and control strategies, understanding hazards and prevention methods for HF corrosion. Introduction to hydrofluoric acid corrosion. Hydrofluoric acid or HF corrosion is one of the most severe challenges in industrial processes due to HF's unique chemical properties and extreme toxicity. Unlike many other acids, HF can dissolve oxides and silicates, making it highly reactive with common construction materials such as carbon steel. This aggressive behavior leads to rapid material degradation, equipment failure, and significant safety hazards. HF corrosion is particularly problematic in alkylation units and other refining processes where HF is used as a catalyst. The acid's ability to penetrate and destroy protective oxide layers means that standard materials fail quickly, necessitating specialized alloys and coatings. Beyond its corrosive nature, HF poses a dual threat because it is highly toxic. Exposure can cause severe burns, systemic toxicity, and even fatalities. Effective management of HF corrosion requires a comprehensive understanding of its chemistry, strict operational controls, and robust safety protocols to prevent catastrophic incidents. Critical factors influencing hydrofluoric acid corrosion. Several factors significantly influence the severity of HF corrosion. High chemical reactivity is the primary driver, as HF aggressively attacks carbon steel and other common materials, especially in the presence of water. Water content is critical. Even small amounts above 1 to 2% can disrupt the protective iron fluoride layer, accelerating corrosion and releasing hydrogen gas, which introduces explosion hazards. Temperature also plays a major role, with corrosion rates increasing at elevated temperatures, often requiring a switch to high-nickel alloys like Monel for service above 70 degrees Celsius. Acid strength is another key parameter. Maintaining HF purity above 88 to 90% helps control corrosion, while impurities such as oxygen can exacerbate damage by destabilizing protective layers. These factors collectively create a highly corrosive environment that demands precise monitoring and control to ensure equipment integrity and operational safety. How hydrofluoric acid attacks materials. The mechanism of HF corrosion involves complex chemical interactions. HF dissolves protective oxide films on metal surfaces, exposing fresh metal to attack. In carbon steel, HF reacts to form iron fluorides, which initially provide some protection but are unstable in the presence of water or oxygen. When water content exceeds critical levels, these protective layers break down, accelerating corrosion and releasing hydrogen gas, which can create explosive conditions. Elevated temperatures further destabilize these layers, increasing corrosion rates and necessitating the use of specialized materials. Unlike other acids, HF's ability to dissolve silicates and oxides means that even glass and ceramic components are vulnerable. This unique mechanism underscores the need for stringent control of process conditions and material selection to mitigate HF's destructive effects. Selecting resistant materials and control strategies including coatings. Material selection is critical for managing HF corrosion. High-nickel alloys such as Monel and Alloy 20 offer superior resistance compared to stainless steels, which fail rapidly in HF environments. In addition to alloy selection, advanced coatings like chemical vapor deposition, CVD, coatings from Silcotech provide inert barriers that protect underlying metal surfaces from HF attack. These coatings are particularly useful in components where alloy upgrades are impractical. Operational strategies complement material selection, including maintaining water content below 1 to 2%, ensuring acid purity above 88%, and preventing oxygen ingress through proper nitrogen blanketing. Together, these measures form a comprehensive approach to controlling HF corrosion and extending equipment life. Best practices for process management, operational controls in hydrofluoric acid alkylation units. HF alkylation units require rigorous operational controls to minimize corrosion risks. Key practices include maintaining water content below 1 to 2%, as even slight increases can dramatically accelerate corrosion. Acid purity should be kept above 88%, as impurities compromise HF stability and increase corrosivity. Temperature management is essential, particularly in vaporizer sections, where excessive heat can destabilize protective layers and necessitate material upgrades. Continuous monitoring for oxygen ingress is also critical, as oxygen contamination disrupts protective fluoride layers and promotes aggressive attack. Implementing these controls, combined with regular inspection and predictive modeling tools, ensures safe and efficient operation in HF service environments. Why hydrofluoric acid is extremely dangerous: dual threat, corrosivity and toxicity. Hydrofluoric acid poses a unique dual threat of extreme corrosivity and toxicity. Despite being classified as a weak acid in aqueous solutions, HF's ability to dissolve glass and oxides makes it highly destructive to industrial materials. From a health perspective, HF exposure is particularly insidious. Burns may not cause immediate pain but result in deep tissue damage, slow healing, and systemic toxicity that can be fatal. Inhalation of HF vapors can lead to severe respiratory distress and death. These hazards necessitate stringent safety protocols, including specialized personal protective equipment, emergency response plans, and continuous monitoring of HF levels in process environments. The combination of material degradation and life-threatening toxicity underscores the importance of comprehensive HF management strategies. Key takeaways for hydrofluoric acid corrosion control. Managing HF corrosion requires a multifaceted approach that addresses both chemical and operational challenges. Critical measures include selecting corrosion-resistant materials such as Monel or Alloy 20, applying advanced coatings, and maintaining strict control over water content, temperature, and acid purity. Operational vigilance is essential, with continuous monitoring for oxygen ingress and adherence to best practices in HF alkylation units. Beyond equipment integrity, safety considerations are paramount due to HF's extreme toxicity, necessitating robust protective measures and emergency protocols. By integrating material science, process control, and safety management, industries can mitigate the risks associated with HF corrosion and ensure reliable, safe operations.